So in the previous lecture, I gave an introduction to Sn2 reactions, and we said that an Sn2 reaction is essentially a reaction between a Lewis acid and the Lewis base. So the Lewis base is called our nucleophile. It attacks a certain atom, displacing our leaving group. So the leaving group is simply an atom or a molecule that is displaced in our Sn2 reaction. Now, we also said that our Sn2 reaction is a reaction between the highest occupied molecular orbital of our Lewis base and the lowest unoccupied orbital of our Lewis acid. So in this lecture, we're going to examine the stereochemistry of our Sn2 reaction. So let's begin by looking at the following examples. So let's suppose we have our nucleophile, our Lewis base, that has the lone pair of electrons, and our Lewis base wants to attack the unoccupied orbital of the atom that's attached to our leaving group. So in this case, it's this carbon atom. Now, this carbon atom is also attached to three other groups. We label them as 1, 2, and 3. And this L simply stands for our leaving group. Now, we want to ask the following question. In what way does the nucleophile approach our carbon atom attached to our leaving group? Does it approach via a backside approach? So does it approach from the back of the leaving group? Or does it approach from the front of the leaving group? Front side approach. Does it approach like so, kicking off the leaving group? Now, before we answer this question, let's look at the following question. What orbitals are interacting? In other words, let's find our highest occupied molecular orbital and our lowest unoccupied molecular orbital in this picture here. So, earlier I said that the HOMO, the highest occupied molecular orbital, is found on our nucleophile. Our two pairs of electrons are found in the non-bonding highest occupied molecular orbital. So, the lone pair of electrons in the highest occupied molecular orbital of the nucleophile, let's assume it's sp3 hybridized. And the LUMO must be somewhere on this atom here. Well, notice since this lone pair of electrons is attacking this carbon atom, which is attached to our leaving group, that means it must be this bond here. But this molecular orbital, the bonding molecular orbital, is already completely filled. And we're looking for an unoccupied molecular orbital. So that means we must be dealing with an anti-bonding molecular orbital. So our LUMO, lowest unoccupied molecular orbital, is our anti-bonding molecular orbital of the Cl bond. So once again, let's examine how we actually build this carbon L bond. So we have the sp3 hybridized orbital of the carbon, and let's say the sp3 hybridized orbital of our leaving group. They interact and produce two different types of molecular orbitals. We have the bonding and anti-bonding. Because the bonding is completely filled, we go to the next unfilled molecular orbital. So that means this is our LUMO. Our lowest unoccupied molecular orbital is the carbon Cl bond, the anti-bonding molecular orbital of the carbon Cl covalent bond. So our HOMO is found on the nucleophile, our LUMO is found on our Cl atom, Cl bond. So let's examine the backside approach and then compare it to the front side approach. Recall that when our atoms form bonds, they form bonds because there's a good overlap between the orbitals. So notice how there's a very good overlap here between these two green lobes and very poor overlap here. So a good bond is formed, a strong bond is formed when there's good overlap. Now, so this is our nucleophile. Our nucleophile, let's say, is sp3 hybridized. So this pair of electrons is inside the sp3 hybridized orbital. And since we just said that our LUMO is the anti-bonding orbital, that means we're dealing with the anti-bonding orbital. So here's our C, our carbon, and our L atom. So our carbon atom and our L atom, they interact, and look at the orbital here. This whole section is a big or large green orbital, and so is this guy. So when they interact, there's good overlap, and that means that the bond formed will be a very strong bond. Remember, good overlap means a strong bond. Okay, so this backside approach seems reasonable because of a good overlap. Let's make sure that we have a different case in the front side approach. So, C, this is what happens if we approach from the front side. So in the front side, there will be what? Well, if we are approaching this way, from this side, or actually from bottom up, our green part, green section of the orbital will interact with these small sections, with this small green section and this small blue section. So, on top of the fact that we'll have a small green section and a large green section, so very poor overlap, there will also be interaction between the blue and the green. So we have bonding interactions, anti-bonding interactions, and the bonding and anti-bonding will cancel one another out, and so we will have no bond whatsoever. So, in the front side approach, the overlap is poor, and we have both bonding and anti-bonding interactions, and these cancel the bond out. So we see that if our nucleophile, if our HOMO, highest occupied molecular orbital of the nucleophile, approaches from the front side, there will be no bond whatsoever. The bonds will cancel. The bonding, anti-bonding will cancel out, and we will have no bond. But if our nucleophile approaches from the back side, there will be very good overlap. And that's exactly what type of approach our molecule, our nucleophile, takes. In an Sn2 reaction, there is always a backside approach. All right. Now let's discuss the inversion of stereochemistry. So, Sn2 reactions always produce inversion. They always undergo inversion in the same way that an umbrella inverts in the wind. Our molecule will invert because when this nucleophile approaches, when this pair of electrons approach this carbon bond, our molecules, our atoms 1, 2, and 3 will invert to this side. And when they invert, they will kick off this L group, this leaving group. And so we will go from this figure to this inverted figure. Notice that our 1, 2, and 3 have been inverted to the other side, and they kicked off this leaving group. Now, as long as the nucleophile and the leaving group have identical Kahn-Ingold pre-log priority numbers, inversion of configuration takes place. And that basically means if our absolute configuration is S on this enantiomer, it will be R on this enantiomer. Now, the reason I say that the nucleophile and leaving group must have the same Kahn-Ingold pre-log priority numbers is that sometimes when these guys are different, we can still have an S to an S and an R to an R. But if this is true, that means we will always go from S to R and from R to S. So, here the only thing we showed was the reactants and the products. What happens in between? What happens when this bond just begins interacting, when this lone pair of electrons just begins interacting with our carbon, and our leaving group begins to leave? What does the picture look like in the middle state? So, let's suppose we have the following example. Let's suppose we have this methyl bromide reacts with our bromine ion. So this lone pair of electrons begins to approach this carbon atom. So our HOMO of this bromine interacts with the LUMO of this carbon Br bond, and our intermediate state, our transition state, looks like this. So right in the middle, we have a symmetrical configuration. In other words, as long as the leaving group and the nucleophile are the same exact atoms, we're going to have a symmetrical depiction like so. So our bond between the carbon and bromine is beginning to break, while our bond between bromine and carbon on this side is beginning to form. And we're right in the middle. You can imagine an umbrella being inverted by the wind, and then you're trying to pull it back. And right in the middle, you're going to look like this. It's going to be a planar molecule. So this HCH bond is 120 degrees, and it's sp2 hybridized. So once it inverts, this bond is broken, and we produce the following product. So we have D, let's say this is D, our reactants, our transition state is Z, and our product is F. So if we label the energy diagram versus reaction, we get the following depiction. So since these are identical, since our leaving and nucleophile groups are identical, D and F will be on the same exact energy level. But because E is an energy maximum, it's a transition state, that means it cannot be isolated, and it exists on an energy maximum. So it will exist on top of this hump. So that means this is a transition state, and it cannot be isolated. So in the transition state for Sn2 reactions, the bonds are sp2 hybridized as long as we have a symmetrical diagram as we have here. So what is the conclusion about our analysis of stereochemistry? Well, Sn2 reactions take place via a backside approach, as we saw here, and undergoes inversion of stereochemistry. So our molecule will always be inverted like we showed before.